So in this video, I want to give a conceptual overview of Pauling's 5 rules. Now, if you have a mineralogy textbook handy, you might want to get that out. Or if you don't have one handy, you could take a look at Pauling's original paper published in 1929, where he expresses those rules, or take a look at his textbook. The second edition was published in 1948. It's called The Nature of the Ionic Bond, and both the 1929 paper and his, at least the second edition of the textbook, are both free. You can download them as PDF files. So the reason for having those out is I want you to be able to read along to see his very specific writing of the various rules, which I'm not going to use here, and you'll see as the video goes on why that's the case. We're just going to give a conceptual overview, kind of a simplification, and a little bit of the meaning behind some of those rules. Right, so let's start off with rule number 1. We'll call it the radius ratio rule. What the radius ratio rule is about is really looking at two things: an efficient packing of atoms in general, but especially of anions. So an efficient packing of atoms and especially of anions. And also it's a way to minimize, it's a way of looking at minimizing anion, let's get this written correctly, anion repulsive forces. So these forces under Pauling's first rule will be minimized. So in terms of the packing, this is an idea that actually goes back to the Braggs, the father and son team that gave us Bragg's law, and also Victor Goldschmidt. He is the namesake of a very famous conference sponsored by the Geochemical Society. These fellows, earlier than Linus Pauling, looked at the way atoms might be packed, and since anions are big and cations are small, you might imagine that anions are going to dominate the space of the structure, and that cations will kind of work their way into the interstices here. So we can think about this limiting size where we can only fit something of a given size in the interstices while most of the space is filled up by these larger anions. So this gives us an efficient packing, which we can derive through geometry, but also by not crowding a cation with too many anions, then we limit anion repulsion. So if we try to squeeze in too many anions fitted around a single cation, then those anions will be overly crowded and we'd have anion repulsive forces that would destabilize the structure. So radius ratio rule is about two of those things: the closest packing idea, and then also minimizing these kinds of repulsive forces. So how about the second rule, rule number 2? That is the electrostatic valence principle. So in this, we'll write it out, electrostatic. So the electrostatic valence principle. This is a way of looking at how anions are locally charged valence given cations that they might be bonded to. So if we have a cation here and another cation here and they're forming bonds with this oxygen, are the bonds that are reaching that oxygen satisfying its charge? So oxygen is typically -2. The most stable state is where the sum of the charges that reach that anion are also adding up to 2, of course positive to balance the negative charge on the anion. It's not just total charge balance, so we can write, for example, SiO2, and of course the entire thing is charge balance. Silicon has a 4+ charge, and we've got a -2 on the oxygen, so we've got a total 8- charge. This is really more about local charge balance. And again, looking in particular at the anions. Then there are rules number 3 and 4, which we can fold together because they're really one and the same thing. Rules 3 and 4 are about minimizing cation repulsive forces. So minimizing cation repulsive forces. So you can see that rules number 1 and 2 are focused on the anion. Now with rules 3 and 4, we're looking at the cations. And in the case of cations, let's erase the chalkboard. Let's take a case where we have, let's say, a silica tetrahedron and another silica tetrahedron over here. And in the middle of those is, well, we're calling it a silica tetrahedron, so it must be a silicon atom. So a silicon atom with a 4+ charge. That's a pretty highly charged cation. As these two tetrahedron come close to one another, there is a certain amount of shielding. So we have oxygens at the corners of these tetrahedra, and they are fairly electron rich, and they allow a little bit of shielding. These oxygens in particular, the way I've drawn it, are shielding those two positive charges, but that shielding is imperfect. And if those two tetrahedra become close enough to one another in terms of their proximity, then we get stronger and stronger repulsive charges between the silicon atoms, the cations that are forming, that are occupying the center of those two sites. So rules 3 and 4 are simply saying that if we're going to have tetrahedra, they can share edges, but they are unlikely to. They're more likely to share corners. If they're going to share corners at all, that keeps a further distance from the cations compared to taking the same tetrahedra and allowing them to share a corner. Let's see if we can draw this. So we have this guy here, and we'll outline it in red. We've got a shared edge right there. So we've got tetrahedral 1, tetrahedral 2, and it's sharing that shared edge. That brings those cations in closer proximity to one another, and that increases the repulsive charge. So if you were to try to do this in a structure, then that edge might break apart and we'd go back to maybe corner sharing, or in many structures, there's no sharing of polyhedral elements at all. And then another corollary to this is that the more highly charged the cation that is occupying that central location in those tetrahedra, then the greater the repulsive charge, and then the less likely you would have shared edges, let alone shared faces, or even shared corners. So 3 and 4 are really all about minimizing those cation repulsions by keeping highly charged cations in these very small polyhedra as separated from one another as possible. And then finally, let's erase the chalkboard again. We have rule number 5, the rule of parsimony. And we'll also look at this in another video. To be parsimonious is to be stingy. And so I think what Linus Pauling is getting at is that crystals are going to build themselves in as simple a way as possible. So they'll build themselves simple structures when possible. Or phrased in another way, the simpler the structures, then to some extent the more stable. And by simple structures, what we really mean here is that there are certain things that are few in number. So let's say we have an octahedron. Let's draw an 8-sided figure here. Oh, let's do that again. So let's say we have something with 8 sides. So here's the top of an octahedron. Here is its bottom part. And then we will let that link up with a tetrahedron. We'll draw that tetrahedron over here. And then maybe that tetrahedron might share corners with another tetrahedron that's over here. So now we can think of constituents in a couple of different ways. We can think of constituents as being the kinds of shared oxygens. We've got a shared oxygen here and another shared oxygen here. Or we can think of the constituents as these polyhedral elements themselves. We have a tetrahedra, we'll call it T2, here's T1, and here's an octahedron over here. And then there are the cations that would occupy the center of these fellows in here, and they could all be different even though I've drawn them in the same color. So the rule of parsimony just means that there's, in most crystals, there's not an unlimited way of having, of arranging these kinds of atoms. They're going to be limited in the kinds of oxygens. Maybe there will only be one type of oxygen where all of them are bonded to similar kinds of cations, or maybe you'll have two types of oxygen. So in this case, we have an oxygen that is linked up to a tetrahedra, and this one to an octahedra. So that could be, we'll call it O1. And then this guy we can call O2. It's linked up to two tetrahedral cations. But it's not going to be an infinite number. There's not going to be, 23 different octahedra. There will be one or two or three types of oxygens, but not much more than that. And the same idea with cations. There will be a couple of different polyhedra. You might have a system, a crystal where there are just tetrahedra and octahedra and nothing else. Maybe you'll have some cubic elements thrown in for good measure, but there aren't going to be an infinite variety or even just a very large number of polyhedra in which cations can be situated in the center of. It'll be a limited number, and they'll be limited in terms of their arrangement. So you'll have arrangements where maybe the octahedra are linked up with each other, or they have a habit of sharing corners with other tetrahedra, but there's not going to be an unlimited variety or even a very large number of ways of making these linkages or having different kinds of atoms occupy different kinds of sites.